LaRouches method and the physical sciences. And before I introduce the speakers and a couple of messages, let me just say literally a couple of words. I think the way to situate precisely this topic, LaRouches method and the physical sciences, is to recognize that the breakthrough that Lyndon LaRouche made in the development of the conception of physical economy and the conception of potential relative population density as the fundamental metric, a breakthrough that he identifies occurring largely in the 48 through 52 period, with the culmination of his work on Riemann and contour, is a breakthrough of the nature, and people should reflect, I think, on the presentations from this standpoint, that makes Lynn the last great thinker in the tradition of Plato, Augustine, Cusa, Leibniz, and so forth. And by being the latest great thinker in that tradition, he becomes, in that sense, the greatest thinker of that tradition. And from his standpoint, from the standpoint of his methodological breakthrough and his actual concrete scientific breakthroughs, we have to rediscover and rethink through all that has gone before to recreate that in our own minds and to allow us to use that breakthrough to develop fundamental science. We need to do this to be able to carry out the policies, the programs, the science drivers, the scientific research and development that is the future of the human species. So I think we have to look at the presentations from that intense a standpoint. Now, before I introduce the first speaker, let me read you a message. Greetings to the conference February 19th. We, students from Poznan, Poland, are acting now as the Polish friends of the Schiller Institute and are sending our greetings and best wishes for the future to all participants of the Schiller Institute conference in Washington. Unfortunately, we are not able to attend personally. The present situation in Poland is very complicated. Although our Prime Minister, Mr. Pawlak, seems to modify the looting policy imposed by the IMF and World Bank, there is still a very strong tendency of liberalism and monetarism in Polish political and government circles. Therefore, we see the necessity to present the ideas of physical economy in these decisive times. We are conscious that our ideas should be spread over the country. So we can happily announce that we just completed a new issue of the Polish newspaper of the Schiller Institute, Nowa Solidarność. Which means new solidarity. And we decided to publish it more regularly now. We are convinced that Polish cultural and historical tradition are a good background for our plans, and that we will find the support of many people in our country, which will make our work even more efficient. At the end, we want to express our congratulations for Lynn's release from prison, and we wish a lot of success for his presidential campaign. Rafał Klopatsky, Andrzej Kozłowski, Małgorzata Krumplewska. Now I want to introduce Jonathan Tennenbaum, who one I know has just completed the recently published program for China. He will speak on axiomatic science and physical economy, a case study, Dmitri Mendeleev and the discovery of the periodic law. Jonathan.
Thank you. The subject I wish to address this afternoon is reflected in the seeming paradox of the existence of two very different, mutually exclusive or contradictory definitions of truth. The first definition or criteria is that exemplified by the schoolboy idea of getting the right answer in the school or equivalent classroom. The right answer relative to some system of textbook knowledge. So that nothing can be accepted as true that contradicts the basic assumptions of that textbook knowledge. So this is the notion of truth expressed, for example, in the practice of cheating at examinations, or learning how to do the experiment so you get the answer which is in the textbook. It's the notion of so-called truth expressed by political correctness, that children should engage in polymorphous sexual perversion in order to demonstrate their acquiescence to what have been defined as the latest axioms of acceptable behavior. In each case, the truth is defined by non-contradiction to some collection of assumptions, either explicit or implicit, which are regarded as completely evident, unassailable, and beyond suspicion. Now, the second conception of truth, the true one, I should argue, is truth as measured against man's continuing existence on this planet. Truth measured in the great laboratory of human history, past, present, and future. So we test the relative truthfulness of our thinking by the success or failure of societies employing that mode of thinking to maintain and expand their existence. Of course, with the proviso that what may appear to be successful in the short term may be the shortest road, the surest road to destruction further down the line. Now, these two definitions or criteria for truth stand in an ironic, contradictory relation to each other. For it is historically demonstrated that in order for man to have existed up to this point, he had to constantly revise, often in a revolutionary way, his knowledge. So, what was at one time defined as true or as the right answer becomes later the wrong answer. Entire chapters of accepted classroom knowledge are eliminated or overthrown. And without that, demonstrably without that, man could not have progressed to more successful ways of existing on this planet. Now, considering these historically demonstrated revolutions, I will speak of an example, we should beware of a trap, of the fallacy of British empiricism. British empiricism admits generally that knowledge does change, but limits the development of knowledge to adding new facts or correcting facts on the basis of sense perception. So, the British idea of truth is to get your facts right, according to the latest authoritative edition of Encyclopedia Britannica in the New York Times. Now, I said that there's a trap there. What is the trap? Well, there's a fallacy underlying this idea of adding facts on the basis of perception, which people often miss. Firstly, in British empiricism, there's no change in the underlying assumptions, the axioms adopted for knowledge. Secondly, there is no such thing as a fact determined by sense perception. The fact is that all sense perception is evaluated by the human mind on the basis of certain ideas in the mind. And those ideas do not come from sense perception, nor are they changed by perception per se. In fact, I may shock you by saying no idea ever came into anyone's mind from the outside, but all ideas are created from inside the mind. Therefore, no progress of knowledge comes as a reaction to sense perception. Progress of knowledge of the sort upon which our existence depends comes uniquely through the process of changing the basic assumptions upon which everything is based, including the way we evaluate so-called facts. We have historical proof that such changes are necessary for human existence. Every society we can document historically, which comes to rely on schoolboy notions of correctness of knowledge, on the equivalent of the Encyclopedia Britannica, is doomed to collapse. Now, this second, truer criteria of the truth, or of the development of human knowledge, which I indicate, presents us with a number of apparent paradoxes. One of these paradoxes might come up in the following sort of question. How can you prove a form of new knowledge which contradicts the basic assumptions of existing knowledge, or maybe your own assumptions? People will ask, well, this new knowledge or these new hypotheses, what can we check it against? Because people habituated to British empiricism and similar modes of schooling always want to check a proposition against something as a reflex to check whether it's the right answer. Well, and then you have another question or paradox. How can I check an idea to find out whether it agrees with human existence on this planet or not? How can I do that? Well, things are not quite so simple. And the problem lies elsewhere than the person is thinking that is formulating the question in that way. The problem is the question of the way of thinking. But let me intensify this paradox with a kind of example which I think will be familiar to many of you. We have someone in front of us, some person, we want to organize that person. And we say, look, the United States is becoming a pure British colony. And the person jumps up and says, that's the most ridiculous thing I've ever heard. What could be more ridiculous as the proposition that the United States is being made into a plantation of British controlled financial system, and that we're all being made slaves to that? So what do? Well, we try to prove what we said by going through the obvious selection of recent events, the clear evidence to prove it. But our friend doesn't see it that way. He or she interprets events in his or her own way. The same facts, the same perceptions are read in a different way, so as to not to arrive at the forbidden conclusions which his or her adopted assumptions forbid them to accept. So we see that no collection of empirical facts, no matter how large, are going to do any good in this case. So we appreciate now the meaning of the statement that the British Empire, like the Venetian one, is an empire of the mind. These people are trapped. They are enslaved in the mind. So, what's the remedy? How do we liberate enslaved minds enslaved in this way? Well, of course, there exists a remedy. Otherwise, we wouldn't exist. Man was not born to be British empiricists. So, to find the answers, or to get on the right path, or fruitful path, I propose that we focus upon the crucial phenomenon called fundamental scientific discovery and its relationship to the desired effect of advancing human existence, that subject matter which is the center of Lin's work. And in order to do that, I want to discuss a kind of a case study. I want to take an example and use it as a kind of Archimedean lever, and I hope that in that way we'll be able to swing ourselves progressively upward to higher levels of insight as the discussion proceeds. Now, I've chosen for this discussion the case of the great Russian scientist Dmitri Mendeleev, born in the 1830s, 1834 I believe, and who died in 1907, and who is known primarily for his discovery of what he called the periodic law of the chemical elements, or perhaps more accurately, the natural system of chemical elements, which is not quite the same thing as the periodic table, which is a simple formal presentation of a result of that natural system. Now, a reason for choosing this particular example is that this discovery of Mendeleev's is central to the whole vast increase of the productive powers of human labor over the period of the last 100 years. That Mendeleev as a person, as a fascinating personality, displays in a very high degree the universal qualities of a scientist in the positive sense, in the second sense, not in the sense of an academic or schoolboy sense, but in the sense of a scientist devoted to building his nation, to building the world. Now, I'm not giving a presentation on chemistry here, and I'm not aiming at being precise in details of chemistry. I want to be as precise as I can about something else, and that is the internal process of discovery, or some crucial features of that process of discovery, which is our, let us say, our experimental data here. Not the chemistry, but the process in the mind. So I have to say, however, a few words about the field of physical chemistry to introduce this. At the time Mendeleev, Dmitri Mendeleev, began his scientific work in 1855, the central axiomatic assumption of chemistry was the notion of a chemical element. This notion is associated with the idea that we cannot differentiate or divide substance down indefinitely without encountering some kind of a limit or a boundary, or as we say, singularity. In the specific practice of chemistry up to the time of Mendeleev, the exploration of this area took the form mainly of what are called separation methods, chemical separation methods, which some of you know if you were fortunate or perhaps unfortunate enough to do school laboratory work in chemistry. Things such as distillation, precipitation, electrolysis, centrifugation, and so forth. Generally speaking, we start with any kind of stuff and we do various things to it to see if we can induce a separation or differentiation of the original stuff into two or more new ones, each having clearly distinct characteristics. So in electrolysis, we produce out of water oxygen and hydrogen, for example. And then we take those new substances, which we produced by the separation of the first one, and we try to do the same thing with each of those two. And we keep doing that, trying to push the process to its most extreme limit of differentiation of matter. Now, through this kind of playful exploration, chemists, in fact, did arrive at a limit, as expected, in the form of what were sometimes called simple bodies or elements, substances which seemingly could no longer be caused to differentiate further. From ancient times, a number of such elements had been identified: iron, copper, tin, lead, mercury, gold, silver, sulfur, carbon. About 5 more elements were added in the period called the Middle Ages. And then, under the influence of Leibniz's work in launching an industrial revolution, there occurred, beginning around the 1740s, and actually during Leibniz's time, an explosive development of physical chemistry. So that at the time Mendeleev graduated from the main pedagogical institute in St. Petersburg, about 64 elements, chemical elements, were known. Now, I should note, however, before going further, that there are different opposing types of hypotheses associated with the term chemical element. British empiricism has insisted, for example, on the supposedly self-evident axiom or idea, which is still repeated, unfortunately, in much of our elementary education, that the elements represent unbreakable ultimate building blocks of matter, whose supposed quality of reality is borrowed from the baby's earliest years in the playpen. The great French chemist Lavoisier, on the contrary, adopted the more adult view that the chemical elements are singularities, are changes, moments of change, in a search not for ultimate building blocks, but for what he called the principles of matter, the principle of generation of matter. And Lavoisier emphasized that the separation methods of chemistry and the result of the so-called simple bodies depends on technology. It's relative, something that may appear to us to be an element or an indivisible substance, later may become divisible through a revolution in technology, which actually occurred through, to a large degree, exactly the work of Mendeleev. Now, I just want to note to you, in reference to what I said before, that this British idea of the building blocks of the unbreakable hard balls or whatever it's represented has the form of an axiomatic assumption. You can't refute it by any experiment or any so-called experimental fact, because if you succeed in separating what appeared to be an element, then they will simply say, oh yeah, well, we just made a mistake in our facts. And this element is actually made up of smaller hard balls, which are irreducible and which are building blocks. And by this process, you get to quarks, and then you get to other things, and you're led down the path toward insanity, which has actually occurred to the majority of physicists following this kind of idea in the endless search for those blocks which they didn't have since they were babies. So, but Lavoisier's conception raises itself a very fruitful paradox. And in the practice of science, we should never try to run away from paradoxes, because where there's a paradox, there's a potential discovery. At the point where we try to define a set of distinct individual principles apparently governing a domain, say the domain of chemistry, at that point that we have identified these principles, we can no longer account for the existence of those principles, for their multitude, and for the relationships between them by the principles themselves. So we can have the elements, but we can't account for why they exist, why they have the properties they have. And exactly the success of chemists in discovering more and more elements ironically underline that paradox. If we look at the development of chemistry up until around 1860, we see an explosion of an accumulation of empirical material, which became what Cantor called a bad infinity. People mixed this and this and this, and then said, well, if we mix it this way, we get that. If we mix it that way, we get that. You had an accumulation of so-called facts without knowledge. And a group of chemists around the circles of Liebig, the great German chemist, and Kekulé, organized in Karlsruhe in Germany in 1860 a conference to put an end to this bad infinity and to introduce new concepts, new hypotheses for chemistry. And so conceptions that had been developed by Ampere in particular, a concept of species of singularities by Ampere and others, was introduced into chemistry in a broad way from 1860. And there was Mendeleev at that conference. Now Mendeleev, his discovery of the periodic system, of the natural system, was provoked by his work as a teacher. And in teaching, he was irritated and provoked by the state of chemistry and asked himself the question, is this really a science, what we're doing here? Can I present this as a science? And Mendeleev wrote the following. He said, quote, "The mere accumulation of facts, even an extremely extensive collection, does not constitute scientific method. It provides neither a direction for further discoveries, nor does it even deserve the name of science in the higher sense of the word. The building the cathedral of science requires not only material, but a design, a plan, harmony. A design for the harmonic composition of parts, and to indicate the pathway by which the most fruitful new material might be generated." Thus, from the very beginning, Mendeleev is not looking for some mere classification or systematization of data, as some, I've often tend to present this, but Mendeleev is looking for a principle, for a method of discovery, for a method of organizing the progress of science and technology. And that's looking for it in the direction of what we call a hereditary principle. Now, what was ironically distinct about the way Mendeleev approached this problem was his insistence on the individuality of each element. And I should just add, for those who might want to consider this point, that there is a crucial difference underlined by Mendeleev between the notion of discreteness, of discrete objects associated with discrete objects, which is really a mathematical notion, and the notion of individuality, which is associated with the Leibniz monad. In any case, Mendeleev emphasized that there is no simple continuity of the sort we associate with continuous motion in visual space, that chemistry, as an experimental domain, reflects the action of something which modifies the ordinary properties of space and imposes a characteristic of what appears to be discontinuous jumps in the manifest properties as we go from one element to the next. That means that we cannot use an ordinary smooth mathematical function, or any of the usual type of mathematical function for this, but we have to use what Leibniz called the method of analysis situs. Now, it's exactly the knowledge of the individuality of the chemical elements, that is, the discontinuity between them, which permits the discovery of the periodic law. Now, very briefly, how did this happen? Well, before Mendeleev, chemists had concentrated on similarities or analogies between the elements. And we can see the first, I've given an example. There were discovered groups of elements which have similar properties, or similar or analogous properties. For example, I've given just some examples. The group of the halogens, chemical elements we call halogens, which include fluoride, fluorine, chlorine, bromine. Another group, they all have similar properties, chemical properties. We have another group called the alkali metals, sodium, potassium, rubidium, which are also very similar. But these two groups, the group of halogens and the group of alkali metals, are completely dissimilar, have completely different properties. So, and I should just point to you, the letters here don't mean really anything. We don't see anything in the letters. You have to be plunged into the process of developing chemistry for the notion of the individuality of these elements to mean anything to you. Now, what did Mendeleev do? Well, he had already begun in his earlier work looking at this notion of the natural groups of elements from a geometrical standpoint. He studied what is called isomorphism of crystals. The fact that one can replace in a crystal elements of a similar group, maintaining the form of the crystal. And then one can consider the jumps or changes of crystal structure as you go from one group of elements to another. So what Mendeleev did, which hadn't really been done before that, is not to look at the similar things alone, but to juxtapose the dissimilar in the manner of Leibniz's analysis situs. And therefore he looked at these two groups and juxtaposed them and compared that with the relative ranking or ordering of elements by means of what is called the atomic weight, which gives a kind of an ordering, a very ironic and paradoxical ordering of the elements according to increasing atomic weight. And when he did that, well, you don't get a clean algebraic mathematical relationship. But Mendeleev he found what he was looking for. What occurred, and we'll listen to his words in just a moment, is that he made a shift in his thinking to say it's not the chemical elements themselves, but is the system, the totality, which is elementary. It's the ordering of the system as a whole which is the actual element, or which we should replace as a notion of elementarity. This is the crucial shift, the shift in thinking of the notion of elementarity. And after that shift comes Mendeleev's essential insight. After that shift, which is his insight, comes the periodic system. It's a shift toward what we would call today in modern language the notion of a negentropic quantum field. Well, we have the testimony of a friend who witnessed Mendeleev in the middle of the struggle to work up the vast material of chemistry into an explicit law. One day the friend stops by to visit Mendeleev in his office, and he sees immediately that Mendeleev, with his very long hair, looks sort of a Beethoven-type figure, is in a state of agony and exhaustion. "What are you working on?" he asks Mendeleev. Mendeleev explains that he had discovered the existence of a periodic system of elements, but had not been able to formulate the law and table. He exclaimed, "Everything is coming together in my head, but I can't express it." Soon afterwards, following 3 days and 3 nights of continuous, unbroken concentration, Mendeleev finally produced his periodic law and the famous table of elements. We can just see the lower, that's part of it. You can raise it up. That's just part of the table. The famous table which bears his name. And he wrote later about this, the whole process. Quote, "The thought was born involuntarily that there must be a connection between mass and chemical elements. And since the mass of material bodies, although it is not an absolute magnitude, but only a relative one, which expresses itself ultimately in the form of atoms, for these reasons it was necessary to search for a functional relationship between the individual characteristics of the individual elements and their atomic weights. When you're searching for something, whether you're looking for mushrooms or for some kind of law, there's no other way than to look and keep trying again. So I wrote down on a collection of cards the names of the elements with their atomic weights and crucial properties, and started to group them according to similar elements and neighboring atomic weights. As soon as I did that, I came to the conclusion that the properties of the elements must be a periodic function of the atomic weight. Although I had doubts about many unclear details, I did not doubt for a minute that the general conclusion was correct." This last comment of Mendeleev is crucial. What Mendeleev now did, and you'll see the group of the halogens and alkali metals in the lower left-hand corner of the table, where he's taken these groups where you have jumps from one group to the other and ordered them, showing the periodic relationship. So what Mendeleev now did was he used his discovery as a yardstick for completely reorganizing and correcting the data of chemistry. In other words, it's the act of discovery, not its literal form, but the act of discovery, which constitutes the elementary superior fact or axiom for reorganizing all of knowledge. So Mendeleev, accordingly, insisted that this new elementarity of the system as a whole must be universal. All of chemistry must obey it with respect to all existing and all future chemical elements. So he tolerated no exceptions. Now, I mentioned that Mendeleev did not find a clean fit, a clean mathematical fit for his law. On the contrary, a great part of the experimental data, of the best experimental data of his time, completely contradicted his periodic law. In about 24 cases, the atomic weights given for the elements indicated that the elements were in the wrong place in the table, the wrong place in the system. They contradicted the system. So, what did Mendeleev do? He could say, oh, my law does not obey the data. No. He said, I have made a discovery. This data is wrong. So he took these about 24 elements with the best measurements of the best chemists of his time, and he simply changed the atomic weights and put them where they should be according to the law. This created an uproar in the chemist community. But Mendeleev was right in every single case. Furthermore, if we look at you'll see, oh, it's all right, it's okay, leave it. You will see there, this is just a copy from part of Mendeleev's original layout, you will see two question marks there, just to the right of aluminium and silicon. There was the third one, which I don't have here, near Bohr. These were just holes, gaps in the table, anomalies. So Mendeleev predicted that there must be, given the universality of the law, there must be elements which will be discovered with the characteristics indicated by their place in the ordering expressed by the table. And Mendeleev used the Sanskrit word eka, which means the next one, and gave names to the undiscovered elements. In the first case, eka aluminium. In the second case, eka silicium, or silicon. And just a few years later, less than 10 years after Mendeleev published detailed prognoses of the properties of these three elements, they were found. 1875, eka aluminium, found by a Frenchman, so he called it gallium. 1879, eka Bohr, found by a Swede who called it scandium. And then finally, 1886, a German found germanium. But there's more. As we follow this process of unfolding the implications of Mendeleev's discovery, we begin to develop the astrophysical implications which are already implicit in the universality of the law which he claimed. That what we're looking at implicitly is a generative process, a process of generation of the elements. Not a British evolutionary scheme, a Darwinian evolution, but we could say, in retrospect, a kind of Vernadskian evolution. Well, for example, if we look at the next one, just the upper one there. This is now just the modern form of the periodic system. You will see I've circled a number of squares there. Those are elements which were not known at the time of Mendeleev, including the whole right-hand column of the so-called noble gases. And I've also in red hatching indicated radioactive elements. And in fact, the discovery of radioactivity was an immediate consequence of Mendeleev's work, and in particular, the work done by Pierre and Marie Curie. Marie Curie, who actually, whose uncle was a student of Mendeleev and who studied in Petersburg, and who did her first experimental work in the laboratory of that student, used the notion of the periodic system to predict that there would be new elements, radioactive elements. Those are the two elements they found of radium and polonium. Now we start to generate more and more anomalies, and a whole new world opens up, a dimension of the isotopes, where the periodic system is expanded but in a coherent way. Well, this led also to the discovery of fission, nuclear fission, in a very lawful way. For example, we have the question why the system, the periodic system, the natural system, seems to end at uranium. It was the heaviest element known up until the 1930s, uranium. So why does it end there as an anomaly of the system? Well, efforts were made to generate elements heavier than uranium, beyond uranium. And what happened? Well, the periodic system responded with fission. It reacted to that attempt with fission. So we got nuclear fission. So the system actually then, however, we can generate heavier elements. We can expand the system in different ways. However, when we do that, we get into new modes. We can't expand it in one mode, but we must go to a new mode of expansion and a new mode of technology. So the periodic system, in Mendeleev's intention, becomes not a scheme of classification of elements, but a method of discovery and continuous expansion. So now let me look back from what I've said at the axiomatics of what Mendeleev did and emphasize a few very crucial points. First, Mendeleev did not arrive at his hypothesis through some kind of inductive reasoning from empirical data. He didn't start by noticing a pattern, as the typical fraudulent British empiricist school or account of scientific discovery would have it. Quite the contrary. The discovery originated with a deliberate, willful act of negating the central axiomatic assumption which had prevailed in the teaching and practice of chemistry at his time, the assumed elementarity of the elements. Instead, he located elementarity in something higher, which was later embodied in the periodic law, but implicitly involves a notion of a principle of generation of the elements, including undiscovered ones, as the quoted remarks of Mendeleev clearly indicate. Second observation, it was only after the original act of insight that Mendeleev threw himself into the chaos of incomplete and contradictory data, and through a Promethean effort forced into the light of day the principle he knew must be there. So he knew what he was looking for. Third point, the result was, in effect, the result of his discovery was a new system of scientific knowledge regarding physical chemistry and implicitly everything else. If we compare the new Mendeleev system of knowledge with the one which existed at his time before the discovery, we find a relationship which is characteristic of fundamental scientific discovery in general. Well, firstly, Mendeleev's new system contains everything useful in the then existing chemical knowledge, but from a vastly more powerful point of view. We don't throw away anything really of substance, except our own clinging to a false assumption. We redefine what we thought we knew from a higher standpoint, and we correct it from that higher standpoint. And then we can look back at the old system and understand many anomalies in that system from the higher standpoint. But at the same time, there's no way to go from the earlier, inferior system to the superior system by some mere deductive or inductive procedure, such as merely filling out the gaps or adding data successively to the older system. The change from the lower to the higher involves throwing out a central axiom and replacing it by a new one, which means a break or discontinuity with the old system of knowledge. The authority of the old system is broken as Mendeleev clearly acts upon that, and a new authority is created. Thus, so to speak, in this business you can't be half pregnant. You either make the jump or you don't. And this point is demonstrated in a very instructive way by the case of Lothar Meyer, who is often a German chemist, who is often regarded as having independently discovered the periodic system, but who actually missed, as far as I can tell, the revolutionary kernel of Mendeleev's discovery. Meyer, in about the same time, had arrived at a superficially similar periodic table by essentially inductive reasoning without challenging the axiomatic assumptions of the old system. Consequently, he neither corrected the wrong values of the atomic weights nor predicted the existence of new elements. In fact, Meyer publicly criticized Mendeleev for what appeared to him, but was not, unwarranted speculation. Meyer could not understand what was the source of Mendeleev's internal authority in going beyond what was provable in Meyer's deductive-inductive terms of reference. And he didn't understand the reason why Mendeleev insisted there can be no exceptions to the natural system. So although Meyer's and Mendeleev's tables are formally similar, the explosion of new scientific discoveries which ensued in the subsequent period flows unambiguously from Mendeleev and not from Lothar Meyer's more timid, half-pregnant approach. So this poses the question, how did Mendeleev know that he was right before he proved it from the data, so to speak? What was his internal authority? That defines the next paradox, which I want to address. It's a paradox also in the sense that we can't solve it by reference only to the immediate circumstances of Mendeleev's discovery. We have to turn our attention to the long waves in the history of science and juxtapose what Mendeleev did to other fundamental discoveries which display a kind of common underlying principle or equivalence. In other words, we shift from looking at the individual fundamental discovery as elementary to a different notion, a notion of higher hypothesis as relatively the more elementary reality of human thought, an evolutionary unity of acts of fundamental discovery. For this purpose, I propose just to briefly turn our attention to the following series of fundamental discoveries. Now, I don't have time to elaborate them, but most of them have been dealt with, at least to a certain extent, in published materials of the Schiller Institute. Firstly, this is in the historical series, the Nicholas of Cusa's insight into the character and implications of the singularity, separating the circle at the higher world of circular action from the inferior linear world of its inscribed polygons. Perhaps we could see the last overhead there. A discovery which is crucial, of Cusa's, crucial to launching the Renaissance. There we see an attempt from the lower circle there, an attempt to arrive at a circle by a process of building polygons with more and more sides. This is familiar to most of you. You build a polygon with more and more sides and try to fill out, so to speak, the circle. But it doesn't work. But I'll come back to that. The second discovery underlying the work of Leonardo da Vinci and Pacioli in conceptualizing the geometrical ordering of living processes and defying the irreducible distinction between living and non-living. Third, Johannes Kepler's founding of a comprehensive physics and astrophysics based on the same notion, which we call today of quantum field, and exemplified by his discovery of the ordering principle, a universal ordering principle of the planetary orbits. And most notable, Kepler's prediction of a missing planet in a gap, in a lawfully determined orbit in his system, which is entirely similar to what Mendeleev did himself. Fourth, Christian Huygens' insight into the implications of a relatively constant speed of light, and directly related to that, the development of the domain of non-algebraic functions by Huygens, Leibniz, Bernoulli, and others. Fifth, the work of Ampere, developing an insight into what are called force-free geometries, creating, in a sense, modern electrodynamics, launching modern electrodynamics, and a technological revolution, followed through by Gauss and Weber. Something which fed directly into, as I mentioned, in the 1860 conference in Karlsruhe, the work of Mendeleev. Mendeleev's discovery itself in this series, and I might mention as a last example the discovery by Planck, Max Planck, a daring and revolutionary hypothesis at that time of the quantum of action. Now I would like to assert, there's not time to go into this here, that if we look into each case in the way I indicated in the case of Mendeleev, we study each one in that way, we'll find that there's a kind of congruence of each and every one of these series of discoveries, even though each one is a highly individual, unrepeatable event. And there's an ordering between these events. Well, we can come to that very readily through Kuhs's discovery, which I'll just reference in following what I said before, that the world of the polygons inscribed in the circle is externally bounded by something, the circle, which can't be reached from the lower world, even in the hypothetical bad infinity elaboration of that lower world, trying to fill in all the spaces of the polygon. Instead, we have to challenge the axioms of the world of polygons, rework them from the standpoint of circular action as elementary, as the elementarity. So what is then primary is what is, so to speak, located in this region between the polygons and the circle. And it's very lawful that the irony of each of these discoveries, each of them involves an irony, that irony comes out, so to speak, is reflected in each case by geometries consistent with circular action and the great circle divisions of the sphere, so-called golden mean harmonics. So you have a recurring theme of the expression of this irony in a similar way, reflecting what you might call the natural language of God's own universe. I might mention that my esteemed colleague Lawrence Hecht began to rework, together with the late Professor Moon, began to rework Mendeleev's discovery and its further implication from the standpoint of this geometrical expression of the underlying irony, the underlying cause of these discoveries, and made a preliminary but very important discovery. Unfortunately, he is hindered right now from continuing his work in the way he would have liked, because he's been thrown into jail for 39 years for supporting the presidential campaigns of Lyndon LaRouche, and he's sitting in jail right now. I just point out that Mendeleev, at the time he made his discovery and his work, became a national hero in Russia. And here it seems, at the moment in the United States, that if somebody discovers something, we throw him into jail. We have to change that. However, it's not enough to simply describe, let us say, or point to this congruence between scientific discoveries from the outside, so to speak. That only identifies an ironically placed location within which the actual substance of the process is located. To get at that, what the substance of the discovery is, we have to relive the flash of insight of the discovery, which inhabits, so to speak, the space between Kuhse's circle and the inferior world of the polygons, that apparently infinitely small or tiny world. And there is inhabits that space the substance of scientific discovery. If we look at the great discoverers of the past, we find, in fact, invariably, among them, a special type of what one might call apprenticeship. I don't mean necessarily apprenticeship to a living person, but a relationship of reliving through a kind of internalization the activity of fundamental discovery of more than one great scientists or thinkers of the past. It's in reliving that process that something is caused to be evoked, to be synthesized in our own minds, which is from generation to generation the immediate cause of fundamental scientific discovery, something we call a higher hypothesis. In the case of Mendeleev, I don't know exactly how this apprenticeship came about. Certainly an important role was played by his studies at the Main Pedagogical Institute in St. Petersburg, which was founded in 1804, and which we have reason to believe was strongly influenced by the ideas of Leibniz, the École Polytechnique, and the Humboldts. This Main Pedagogical Institute, which trained teachers for the gymnasia in Russia, grouped together some of the most extraordinary scientific thinkers in Russia at that time, particularly Mendeleev's teacher, the chemist A.A. Voskresensky. Voskresensky focused his pedagogy on what he called the battle of ideas in science. But there's another crucial piece of evidence, I think, demonstrating the higher hypothesis underlying Mendeleev's work, which is the way he reacted to a typical British operation against continental science. This is the case of the well-known British physicist Crookes, who in 1886 gave speeches and circulated writings about his supposed hypothesis on the existence of a primordial form of material, of matter, which he called protilla, out of which all elements are supposedly formed. This was nothing more than a warmed-over version of Aristotle's old first matter, a shapeless, featureless goo, which generates a kind of foam out of which everything is supposed to come. And Crookes made two arguments which were unfortunately plausible to some people at that time. He argued that the periodic law of Mendeleev pointed to the unity of all forms of matter, and also to a process of evolution of matter, paralleling the evolution of animal species. And since, watch out, evolution proceeds from the simpler to the complex, everything must originate from a single form of the simplest matter, something that has no features whatsoever. This protilla or primordial goo, which you could call the goo-goo. If you go to the Princeton mathematics department, they're already discussing the theory of the goo-goo, which is called the goo-goo-goo. In any case, in many Russian circles, scientific circles, there was a certain attraction to this idea. And Mendeleev, he hit the ceiling. He was furious, and he attacked Crookes violently for reasons which many of his colleagues, unfortunately, did not comprehend. Here's a quote from a colleague of Mendeleev's. "It's strange that Dmitri Mendeleev protested against this approach of Crookes, which was based on Mendeleev's own periodic law. I remember vividly how, after a very lively meeting of the Physical Society, we three, Dmitri Ivanovich, Stoletov, and I, argued into late at night over this question, which at that time everyone was thinking about, thanks to the brochure by Crookes. Throwing forward all his objections, Dmitri Ivanovich, whose familiar wide modulations of voice from the lowest bass to the almost unsingable high notes signaled to those who knew him that he was becoming angry, began to turn his arguments literally ad hominem. Alexander Grigorovich, Clementy Arkadyevich, I beg your pardon. Surely you are able to recognize your own individual identity. Please permit also the elements cobalt and nickel to have their own personalities. We looked at each other and changed the subject. It goes to the point. What's the point here? It's the Parmenides paradox. You can't solve the problem of reconciling the one and the many. You can't explain the existence of individuality except from the standpoint of higher hypothesis. That is, from the standpoint of that action which carries us through a series of fundamental scientific revolutions, each of which involves an axiomatic discontinuity, a jump of the sort we've indicated. Nothing less than this type of action can qualify to be considered as a candidate for primordial substance, or for substance at all. If you introduce into science a species of a notion of fundamental substance which is representable as an object of sense imagination, it's tiny hard balls, building blocks, or the primordial goo of Crookes, or any such notion that's compatible with a fixed formal axiomatic system, if you do that, then you automatically collapse the process of scientific discovery, because the mind of the scientist becomes stuck in the axiomatic system of that quality, and he's lost his grip on the higher hypothesis. Well, now, in closing, I might mention that Mendeleev, in addition to his denunciation of Crookes' fundamental substance, remarked that to the extent the elements are divisible into some sort of subatomic particles, people should remember that putting together those in some kind of reaction, you can call it fusion, but whatever, the mass of the resulting nucleus will be different from the masses of the parts that you combined in this reaction. That is, of course, completely ununderstandable from the standpoint of any simple notion of substance. So, in closing, I want to pose the question of proof. How did Mendeleev know that his hypothesis is a truthful one, let us say, in advance, before it's elaborated? The answer, in essence, is simple, that the truthfulness of a discovery, of an individual discovery, resides essentially in the higher hypothesis which generated it, which is actualized in this flash of insight which we described. A true, or relatively true, higher hypothesis is proved not by any individual laboratory experiment or an individual discovery, but by physical economy, by its effect in providing the basis for a physically negentropic development of human society into the potentially indefinite future. So the history of the last 550 years, the last period since Couse, has demonstrated in the great burst of human creativity and productivity, relative to any other period, the superiority or relative truth of the higher hypothesis from which Mendeleev and others derived their discoveries. And Mendeleev's life work is completely coherent with this relationship to physical economy. His life spans the period between the Russian-American alliance of the 1860s to the efforts of Sergei Witte, period of the attempted, or the actually relatively successful initial industrialization of Russia. And Mendeleev was really the dynamo of the industrial development of Russia in collaboration with Europe. His early work was in agricultural chemistry, continuing the work of Liebig. He ran experimental farms and other activities. He played a crucial role in developing the petrochemical industry in Baku. He made an official visit to the United States in 1876, the Philadelphia Centenary celebration. He has a close relationship to the American Chemical School, leading to Harkins. He developed the industrial region of the Urals. Then his collaboration with Witte, his works on economics, particularly his 700-page treatise on the tariff, showing his studies of List and so forth. Also, his role in defending the industrial system against various kinds of Russia, against various kinds of attacks. For example, the Spiritism, which was spread by the British all over, the parapsychology, in fact, spread by the same crooked crooks, which I mentioned before. So Mendeleev represents a kind of a Promethean scientist, a nation builder of a similar sort, perhaps, as Benjamin Franklin. It would be important to investigate carefully what happened to the scientific tradition exemplified by Mendeleev in Russia, in Ukraine, and so forth over the last 100 years. Scientific institutions of Russia and Ukraine continued to produce a great number of brilliant and excellent scientists and engineers, rivaling certainly anything abroad in that period. Particularly, I would mention Vernadsky, another universal scientific mind, figures such as Alexander Gorovich and so forth. But at the same time, we see, especially in the last 25 years, a clear decline. We see a corrupting influence of an overemphasis on mathematical formalism, on sterile classroom and textbook forms of education, competitive examination systems, as opposed to the kind of apprenticeship type of education which apparently Mendeleev had. The influence of systems analysis as a formal doctrine, of the kind of economic theory of so-called theory of von Neumann. And on the other side, particularly into the 1950s, the Hegelian injection of Hegelian ideas exemplified by the promotion of the so-called law of transformation of quantity into quality, which is a complete mystification of Mendeleev's method. So we see that the scientific and intellectual leadership has been crippled in the East by mainly British influence, parallel to what happened in the West. So what we most urgently need, I think, is the emergence of a new leadership in Russia and other nations which understands the kinds of things we've been discussing. Might we not imagine, in the not-too-distant future, a revival of the alliance between Russia, America, and continental Europe against the evil represented by the British Empire of the mind? A revival of the Russian-American alliance of the 1860s against Britain, which was essential to the environment in which Mendeleev worked, of which he was a part. Why should we allow ourselves to be destroyed? For what? For the sake of the peep show at Buckingham Palace? Might we not rather unleash once again the forces of scientific and technological progress through such things as the coming colonization of Mars, the realization of controlled nuclear fusion, and other forms of nuclear processes implicit in Mendeleev's work, through rebuilding the infrastructure basis of the world economy? By counterposing the notion of Platonic higher hypothesis to the various varieties of British empiricism now destroying the world, we realize that there's a higher level of mental activity which generates the change, the improvement of the method by which we exist. A movement toward a more perfect higher hypothesis. In a sense, toward an intellectually and morally more perfect human race, in practice. That is hypothesizing the higher hypothesis, the kind of activity which Lin and LaRouche exemplifies. The possibility of defeating the empire of the mind and of saving the human race rests on that kind of Socratic knowledge, the kind of knowledge that Lin has given us. So, as thankful apprentices, we want to end by wishing Lin many more years of fruitful and productive life. Thank you.
Let me announce that the panelists on tomorrow morning's panel, the Palmerston Zoo, should come meet briefly at the podium here at the end of the session. That's all 8 of you or whatever. I also have another greeting, this one from Zagreb in Croatia. Dear friends, please accept my wishes for the successful and fruitful conference. Let me say that the efforts of the people of the Schiller Institute are and have been remarkable. I appreciate very much your activities, especially in explaining our world, but also in bringing new lights into the drama we are living in. If I may mention, the World Society of Victimology is trying to help to avoid victimization in our societies and to improve human rights for the victims of crime and victims of abuse of power. If I may suggest, please raise the protest against the aggressive war started by Serbia and ask for peace in Bosnia-Herzegovina. After seeing citizens of Sarajevo dying, starving, especially children, after my return from Sarajevo, I have proposed to all responsible to establish the airlift for the dying in Sarajevo. Please accept this appeal and support it. It might save the life of many of the 350,000 citizens of the besieged city of Sarajevo. God bless you. Sincerely, Dr. Zvonimir Paul Tsaparovich. Now, before the introduction, this morning we had a number of guests introduced from Russia and Eastern Europe, and we can move to the East. I think hopefully we have some people here, first of all from India, Mr. P.P. Gurung of the All India Congress Working Committee, if he's here. And Dr. Rajiv Tyagi and his wife, Mrs. Tyagi, both medical doctors from India. Dr. Tyagi is also a leading activist in the Congress Party, if they're here. Please, if you're here, stand up. Now, we also have a number of guests, I won't go through, but a number of guests from China, representing exiles from Beijing, from Shanghai, from Chengdu in Sichuan province, and from Guangzhou. If they could stand up. Also, Niu Shen, who's one of the leaders of the Party for Freedom and Democracy, was a political prisoner for 5 years in China. And I won't go through all the individuals, but we also have, continuing in this area of the world, we have 22 fair dinkum blokes from Australia who have been here. If they could stand up. And many of the Australian members will be staying in the United States to organize in various parts of the country over, I believe, about the next month. So we should have good fun. Okay, and now the next speaker is Dino De Paoli, who will speak on astronomy as a sort of a textbook case of the failure of mathematical space-time to explain causality.
Again, there is a mistake. It's not astronomy, it's witchcraft, how you will say. I would like to start by indicating that the absurdity of our present culture situation is well illustrated by the recent opinion of some so-called scientists who not only consider useless the colonization of our planetary system, but also opposes space-based telescopic observation. The reason given by such brilliant brain is that with modern computer, we would easily be able to replicate models of our physical universe and work with them in virtual space instead of messing out in the real one. That's an American from Boston. It's not worth here to spend too much time on such insanities. we experience daily the absurdity of the so-called computer-generated models. The models for the warm age, the ozone age, recently the ice age, etc. The effect on the population of predictions based on such a model in reality is quite paradoxical. People do not believe anymore such models. Like people at certain point did not believe anymore the Oracle of Delphi. But perhaps that is the aim of the full operation. The idea is to induce people to believe that you cannot trust anything anymore, that nothing is secure. We are again in the world of populism, of faith in opinion, in demagogy, the world of your grandmother, or my grandmother, which is more famous, who, as you remember, always told you, watch out, kid, you never know. In short, the world of magic. It's well known throughout history that the dominance of formal thinking, because it cannot make intelligible the actual causality of events, kills the notion of real intellectual rigor, kills the conscient awareness in people of creative processes. The net result is to leave the domain of the so-called unknown in the end of witchcrafts. The universe becomes full of holes, like the modern theories of chaos, holes very similar to the wizard's head. Or in more brutal words, one could say that a modern scientist is just a constipated astrologer who has substituted a computer to the crystal ball. The fact that formalism and mechanicism cannot be the base for any scientific knowledge has been proved many times and in a definitive way in the 1930s by Kurt Gödel. But to simply prove the limit of formalism is not enough. The trouble and real difficulty is on grasping the real implication of that mysterium, which seems always to escape any formalization. That mysterium which escapes any attempt to have complete theories and consistent models. Till the work of Gödel, the positivist, materialist, etc., could pretend that everything in the universe could be reduced to a simple computation. Nothing could exist which would not be material and could not be computed. After the work of Gödel, such belief is impossible as to believe that we can square the circle. So the issue becomes to try to narrow down what is that ghost which passed through any net of mathematical logical computation, no matter how fine is the net used. What is the phase of real causality which operates in space-time? When we have in front of our eyes the issue of the circle and the polygons, as Jonathan showed before, we are easily misled by the fact that we see the circle as a visible object, although we cannot prove its existence by linear measurements through the polygons. But when we operate with the causality which cannot be measured with no instrument of visual space-time, and so cannot be made visible, the issue becomes much more difficult to grasp. Contrary to what you think, the belief in the ghosts, in the mysterium tremendum, is not to be found among normal religious people, but among most of today's university academicians, although they call themselves agnostics, or even other more complicated names. After the 1930s, after the discovery of quantum mechanics, we saw more and more university academicians going back to read the secret books of the Rosicrucians instead of doing some work. It's enough to look at the biographies of Bohr, Pauli, Turing, Russell, to see that once the mask of logical formalism and materialism is broken, under it appears the mask of the brothers who are still looking for the lost name. the mysterium tremendissimo of the Gnosticism. If one would read the letter of St. Paul to the Athenians concerning the issue of the unknown God, one would grasp easily and profoundly why scientific thought found a so fertile ground inside the culture of Christianity. "Two shall not kill," was said this morning. It's clear, or should be so. But to discover that this is not enough, and that you need also to love with all your mind, with all your heart, and with all yourself. To discover this, it needed quite an extraordinary intervention 1994 years ago. And I should advise you to reflect quietly by yourself about the nominal contradiction, love with your mind. For this reason, I proposed that the 6th of January be named the Day of Science. As you remember, that was when the three astrologers went to bow in front of the newborn truthfulness. LaRouches developed this morning, and in recent writings, the real implication to be derived from the impossibility of any formal model to replicate or even approximate the process of creativity, and so even less the process of creation. I do not need to repeat it. I can limit myself to illustrate one point of it. I would like to use as pedagogical device the work of someone relatively unknown to you, Blaise Pascal, a French scientist who lived at the end of the 17th century. He is the actual inventor of the principle of modern computers. He is also the crucial inspirator of the geometrical work of Leibniz, as well as of Monge. Cantor studied him very carefully, so as you can see, he was a crucial chain in the reproduction and improvement of the scientific thinking. But he also was a philosopher, a deep religious person, and a theologian. He mastered not only the work of Kepler and Leonardo, but also of Cusa. It will take a full conference to illustrate all his work. And that's not my aim. My aim is to use only one of his reflections as the underlying theme of my presentation. Pascal, in some modern textbook, is considered part of the existentialist school because he wrote the famous and poetic sentence, quote, "The eternal silence of the infinite space frightens me." A lot of people obviously tend to share such emotion, although silence is a rare event in our world today. But Pascal also added something else, with which people will have more difficulty to cope. Quote, "It is not in space that I have to look to find my dignity, but in the ordering of my thinking. As a simple space, the universe grasps me and swallows me like a point. But as reason, I grasp and comprehend it." Most of modern culture has lost this sense of inner transcendental power, such divine gift present in human beings, and which makes man to be a singular event if related to simple space-time or biological processes. To grasp this, it's the beginning of any decent thinking. To illustrate what's said above, we will have to take a long trip. Last time here, as you remember, at least some one of you, I spoke about the discovery of long cycles in our planetary system. That is the invention of the calendar, or the refutation of astrology. Now I will go a bit further. Can I have the light off, please? Is it visible? That's our sun, so much loved by our ecologists. But if they would know that this is just a big nuclear power, they will try probably to shut it off. Now this is a drawing. This is the way our ordered planetary system would look like if we could see its electromagnetic structure. Now we turn off the light, the sun. It's at night and we can look up the sky. There we see something which we should know, the Milky Way. Beautiful, but extremely messy, or at least looks so. With it's millions of sun. Actually, the number of the star in it's over 200 billions. Now, I don't know if you can see anything there. I hope so. Still, the human mind look and find some kind of order. Some of you, which is experienced the looked star, can recognize easily what is shown there. That's the constellation of Orion. I have not the point. I cannot point out what I wanted, but so you have to use some imagination. But that's Orion, as you can see it with your naked eyes. But now let's go up. Let's go inside the Milky Way and let's go to see how the stars are born. Here we see now the nebula inside Orion. That's the Orion Nebula. It's extremely near to us, only 1,500 light years. Now you should just know that the light can travel 6,000 billion miles in 1 year. Such type of nebula is a beautiful laboratory. There is where the stars are constructed. This is one inner part of the Orion Nebula. That's one place where we see the production of stars. Now we go even more inside that. And there you see the beautiful green color of oxygen. Now think about what Jonathan just presented about chemical elements. That's oxygen. The air is packed with all kinds of inorganic and organic products, including ammonia. There in Orion we have extremely young star, 500,000 years old. And some, if it's confirmed, it's only 2,000 years old. That's the other part of the Orion Nebula, which is at the beginning as a totality. Now all this, as I said, you can see basically the simple binocular, not these details, but the essential of this nebula. Now look at that horse head. I don't know, I can't indicate, unfortunately, but it's very visible. That's another part of the same nebula. But that dark horse head is actually where a shock wave is producing eddies, like a slowly spinning ball of gas, which will condensate and formation of new stars. So very near to us, there is a lot of activity going on. Now let's visit other factories and laboratories all the time just inside our so-called Milky Way. That's another one of these factories, the Rosetta Nebula. It's only 6,000 light years away from us. Inside you see again production of star. Eta Carina. You have to go to in the south, to look in the south to find it. You can see basically a shock wave, very specific demarcation in the nebula, and shock waves, and again another big factory and moreover, not yet submitted to free market economy. So it still produces something. Now let's go to the south. In Sagittarius areas, this is the Eagle Nebula, another star producer. The Lagoon Nebula, another one. All factories. Trifid Nebula. We are all the time around 5,000 light years. All the time, or what I've presented till now. Let's stay inside the Milky Way, but look for other types of star factories. Now, I don't know if you can see this. This is again with our simple. I don't know if you're able to see anything, but otherwise you can simply tonight look at the star by yourself, and you will see easily what's called the Pleiades on the right, and on the left what's called the constellation of Taurus, which is extremely near to us. It's the nearest. It's only 60 light years. In that area you have the so-called open globular clusters, open clusters, the Pleiad and the Hyades. Now let's see one of them with the telescope to see what it means. That's what it means. It's basically another type of formation of stars. You can see the blue color again there, typical of these situations. Now, if tonight you have some time and you have a binocular, just look in the direction of Cancer, and you will see a beautiful one called the Precep of this type of star formation. Now let's see some factory which is closing down. These are the so-called globular cluster. Again, in our Milky Way, they are much older, bigger. They are billions of years old and formed by millions of stars like this one here, which is in Hercules. They are a bit like dying elephant. They are sterile and they have orbits extremely slow, going away from our Milky Way. So the stars are not only born, but also they die, as we just are seeing. But there are interesting rests of this phenomena, what are called the planetary nebulas. It is the dying of stars. Here we see one which exploded 50,000 years ago. Still there, something. This is also another one, 20,000 years ago, exploded. And that is the most famous one, at least should be. It's called the Crab Nebula, not for food. It exploded in the year 1054 and was recorded by Chinese, American Indians, Arabs, etc. Such explosions are usually a major event and moreover creates troubles for our astrologers, given that suddenly one star of their zodiac disappears. This happened during the Renaissance and was remarked by Tycho Brahe. It's now time to grasp that the apparent disordered mass of stars, which we call the Milky Way, so rich in factories, so rich in life and death, it's after all not so disordered. If only we could see it not from under, but from above. Given our budgetary constraint for the moment, we cannot go to take a picture from outside. But we know how it really looks like. This is a drawing of it, a beautiful spiral, quite an ordered things. As said, unfortunately, I cannot indicate it, but at the end, in the outside arm of the spiral, it's where we are. That's where our sun is. That's where our ordered planetary system is. just in one arm, very small part. At that small part of the arm, it what before we called the Milky Way, and it looked very disordered. In reality, it's a very ordered cycle. And in reality, the ordered cycles of our planetary system, our calendar, so to speak, depends entirely on the activity of the galaxies as a whole. A beautiful bounded unity. We are rotating around its center in about 200 million years. But we are not alone. That's another lateral drawing of the galaxies. And the position of the sun is just at the extreme of it. We are not alone. These galaxies as satellites, as our Earth, as the moon for satellites. The biggest satellites you can see with your own eyes. It's called the Large Magellanic Cloud. You have to get invited in Australia or Latin America to see it. It's also another small spiral galaxies. And inside it you see other nebulas as on the top. That is other stars factory, like our Orion. That's called the Tarantula Nebula. That's another satellite of our galaxies. That is galaxies which has as satellites other smaller galaxies. That's called the Small Magellanic Cloud, also in the south. 200,000 light years away, very rich in young star. But we have not only satellites. As the Earth has companion planets, so our own galaxies have companion galaxies. The most important and easy to see with your own naked eyes is Andromeda. Now it's a bit difficult, but you have to wait for another season. And you can see in Andromeda, which is extremely near to us, the satellites of Andromeda, two other small galaxies, which can indicate which are the satellite of Andromedas. Now the interesting thing, which I think you should really grasp, is that Andromeda and our own galaxies have a common bounding. It's a kind of duet. Have a common bounding field, which make one of them to rotate clockwise, while the other counter-rotates. That is a bit like the photo which I'm going to show now, just as an example. So one of this is just a meteorological photo, but this would be the same as what's happening to the galaxies. That while our own galaxies and the satellites have a clockwise rotation, Andromeda and these own galaxies has a counterclockwise rotation, which is the best proof of a common higher field, so to speak, for their own ordering. So the galaxies is an evolutionary system with the central region a nucleus and often spiral arms and spherical corona. The arms, as we saw in the case of our Milky Way, is a laboratory of chemical production. Near the nucleus, the rotation takes 20 million years. In the outer layers, 200 millions. I want just to show you some samples of these galaxies. The first one here is 10 million light year away. This is in Ursa Major. This one, the same distance, another type of galaxies, extremely beautiful. Most of them seem to be spiral. That's a bit different. Now, the thing you should get in mind, that galaxies are not dead objects, as I showed you before. They are source of enormous amount of energy, which will terrorize any romantic ecologist. You can see here some visual impression of the core of one of these galaxies, in Centaurus. or this one. You can see very easily from the photo the extremely high level density energy in the core of the galaxies. Now, at this point, you probably begin to suspect that this is not the end of our story, that galaxies are not dead atoms in empty space, as our planets are not symbol balls interacting in empty space. They are bounded, and they harmonically relate to each other as if dancing nice music. Let me give you a first very simple example of what I mean with harmonic bounding, first of all, before going further. I don't know if you can see it here, it's actually upside down, but doesn't matter. You can still understand what I want to say. This is water waves, a photograph of water waves, and you see the nodal points of the water waves. Now, the distribution, so-called harmonic distribution, the relation of this nodal point, it's determined by the global behavior of the waves and their so-called external bounding conditions. That's the same thing happen on a string or any other wave or any other so-called field. Back to our galaxies now, keeping that in mind. Here you see the interaction of two galaxies, M51, Messier 51. I don't know if it's clear from this photo, but this next one will be even more clear. And now, in honor of Beethoven, we have the Stefan Quintet. Now, at this point of my pictures, we are showing galaxies with distance from 15 to 60 million light years. Now, remember what I said at the beginning, what is a light year? And we can go much, much further. We begin soon to lose the sense of space in terms of symbol numbers. But here, too, we still discover ordered systems, familiar phases like our planetary system, but this time composed of galaxies. Actually, the ordering of our planetary system depends by the bounding condition, which gather together such families of galaxies. And they are old-fashioned families, not educated to the OBE, so they tend to be quite patriarchally organized. Here are some examples. This is the so-called Virgo cluster, 70 million light years away. And I leave to you and to your imagination to see what's the ordering there. Now, as I said before, each galaxies have billions of solar systems. Now, this is so far away that even with the telescope, you get this kind of photos. This is the Hercules cluster, 700 million light years away. And you see how many galaxies look like under a microscope, actually. Isn't it funny? It's itself just part of a higher supercluster. And we could find supercluster if we want, etc., 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 etc. Till billions of light years away, we have till now counted hundreds of billions of galaxies, a number too big even for George Soros to speculate with. This is a map of just 1 million galaxies. Quite an interesting organic unity. But please, don't focus on the circle there. That is the only thing which is fictitious. As you realized, we are not observing. You can turn on the light, please, now. As you realized, we are not observing simple distance in space. We are actually mapping time. we are looking at our own past. When you will look at the star tonight, as I hope, you will be looking at Sirius. In reality, you see what happened 9 years ago. You will see Polaris. There you see what happened during the construction of the Gothic cathedrals. When you look at Andromeda, you are looking at our prehistoric age. Because our universe changes, and only because it changes, we can learn something from looking at such past events. But now comes the question, what actually does bounds the universe then? What is at the end of that etc., 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 etc.? There is a final super cluster, which can we see? Well, you can publicly ask that question tomorrow afternoon in the question period, and somebody else will probably respond it for me, in case you still need an answer. Can we look at the universe from above as we looked at our galaxies from above? I guess Blaise Pascal answered already that question when we started this presentation. It's necessary, nevertheless, to master the work of Cantor, to make the answer a bit more precise. There is no possible final object in space-time which we can identify as a bounding causality. The absolute, as Cantor called that situation, it's not there to be seen as an object, cannot be reduced to none of the elements which it bounds. The absolute as a necessary and sufficient causality is an attribute of God, not of space-time, said Cantor. To miss this has been the constant mistake of all pantheists, from some of the pre-Socratic to Hegel via Aristotle. This is the base of the Parmenides paradox. And this is not just a metaphysical issue, but the key element of any process of discovery which have characterized our history. This is the reason why Plato, as they say, put at the center of his mathematical teaching the issue of the intelligibility of the incommensurable relations. This has to be seen as a two-step side problem. First, one has to grasp the impossibility of measure the bounding with what it's bounded, as Jonathan showed before on the case of the circle and the polygon. And that's the most famous example of such impossibility, called the impossibility of squaring the circle. But there is a second step to grasp. That's not enough. One has to establish, nevertheless, an intelligible relation between these two different species. That is, we have to establish some kind of so-called irrational or transcendental function, as they are called in mathematics today. This was done in particular by Plato and formalized by one of his students and direct successor, contrary to the myth of Aristotle, is the direct successor to the academy, that is Eudoxus. Given that we have many times discussed the first issue, that is the squaring of the circle, I want to focus shortly and as conclusion to the second aspect, that is the intelligibility of a transcendental relation. Can I have the overhead, please? Now, I want just to give you a very quick set of examples without going in any detail. A very early example of incommensurability appeared in the impossibility to relate numerically the diagonal to the side of the square, as you know from your school. I don't need to repeat it. But it can be done geometrically through the Pythagorean construction. As you know, if you have the sides 1, the diagonal of that triangle is something called the square root of 2, which is an irrational number. Now, what I'm interested in one construction which Plato presented in one of his dialogue. he presented a geometrical construction to order a set of such irrationality. And that's the construction which he did in the upper part. Now there you see very easily that if AB is 1 and BC is 1, the diagonal, that is AC, is square root of 2. And now if you're a bit smart, you can go on and see that CD is also 1, and that AD is square root of 3. AE is square root of 4, AF is square root of 5, AG is square root of 7, and so on and so on. You have a very simple example of ordering of one type, one common type of irrationalities or irrational numbers, geometrically constructed. If you do not understand the details, you can ask your respective leaders in the locals. Now, let me give you a second example of the same type of problem. Can I go back to the slide, please? Oh yeah, I have it, okay. Doesn't come anything. Just go ahead, it comes now, the next. Oh, look it up. So, just at the end of the first, where I had stopped, then there is no number. Now let me, in the meantime that we are looking for my slides, I would like to introduce the second type of problem as an example. You have to go to the end of this, basically. Yeah. So that is what's called the projective plane, projective space. Now you know it from your own school that it is impossible to map a complete sphere on a plane, as you can see from any geographic map, the distortion which you obtain. The reason is that the plane is missing one point in respect to the sphere. Further. We go after the universe. Here it is. So, this is an example of what you learn in any school, that if you try to map a sphere on a plane, there is one missing point, only one missing point on the plane compared to the sphere. You are not able to represent the sphere fully on the plane. Now, still, as we saw for the case of the Pythagorean system, it was discovered during the Italian Renaissance that we can create a special plane called the projective plane, which has the same function as we saw on this geometrical spiral, that is to make intelligible, to have a metaphor or a transcendental function of such impossibility of representation. The projective plane, again, without any details, and in the locals you have many experienced people to go through this, you can see that the projective plane is the one in the center. We construct a special point, which is the point O on top, which is not really part of the plane. But nevertheless, this point, which is called point at infinity, defines the full harmonic metric in the plane. You can see this in the next slide. Here. That point there, B, even if it's represented there, you can never reach it. That's called a point at infinity, and it is not part of the plane. It's not the same as all the other points in the plane. But it is the point which defines the bounding condition, that is, defines the harmonic distribution inside the plane. Now you can see it here, because we are keeping at the level of image, in the case of Leonardo, how we use that point. You see that the point at infinity is put outside of the face, and Leonardo is indicating how that point at infinity, that limiting point, or that limit, is defining the harmonic ratios of the human body, that is golden means ratio or other type of ratios, which are defining the metric of space-time. Such point is what in modern mathematics is called a limit, or Cantor will use as example of a transfinite point. Here you cannot see anything, but if you could see it, you would see the plane completely and metrically, so to speak, harmonically divided by a set of 3 of such limiting point at infinity, or such transfinite points. That's an important variation which Leonardo introduced, caused by the realization of physical property of light, which I cannot go in any details here, but you see that the so-called points breaks down, and not anymore even points, the so-called point at infinity. I just want to show you now, as concluding this example, just some practical application of this. As you know, it was used as byproduct in painting as defining the optical vision in the painting. You see a Leonardo you're using to define the metric distance in painting for the perspective. And there you see some final result of that. Okay, that's the slides. Now, let me conclude with the third example of the same type of problem, which I just described, with the point at infinity and with the Plato function. It's called the Leibnizian transcendental function. In 1775, in De Vera Proportione Circuli, Leibniz approached the problem of the infinite series, which appear in any attempt to relate incommensurable numerically. As you saw, all the time when we are handling this kind of paradoxes, the infinite series appear all the time, from space to geometry and any other series. But Leibniz, taking up the concept which Plato, Cusa, and others had developed, realized, against the dominant opinion of the people around him, that the issue was not to focus on the infinite series per se and to attempt to reach its limit at the end of the series with some artifact. Instead, he said, quote, "If we consider the totality of the series, even if infinite, as long as it's defined by some law of progression, then we can conceive it as a totality, even if not expressible by a symbol number." For symbol number, I meant your common 1, 2, 3, or any finite combination of them. Such unity of multiplicity, such idea, as Plato called them, such new number, Leibniz called transcendental numbers, or functions. They are nothing but the same type of the harmonic unity defined by this limiting bounding condition obtained in the projective plane to the point at infinity, as we saw. As you have noticed, from all the previous example, we have had to do all the time with infinite series whose maximum, whose ordering, or whose bounding was never of the same type as the element of the series. The misunderstanding of this point led to the blunder of Cauchy, which reappears in modern calculus, and leads to all kind of blunder in modern formal logic as well as in all other areas, as expressed by Russell and others, which I, for time reason, will skip, so I just mention nominally how this arrived to this kind of paradoxes. Cantor, Georg Cantor, not only will grasp fully the mistake done by Cauchy and will correct it, but going back explicitly and directly to Plato, Kuhn, and Leibniz. Moreover, it will develop the way to define precisely the notion of increasing power of such higher type of orderings, whose bounding then is located on what he called the absolute. That is, implicitly, he proved that we can have a higher ordering principle of transcendental functions, but that nevertheless, there is no way to represent that with any type of mathematical function, the full universe once for all. I can't develop any detail of all this, but I would like to add that, and this should have become obvious to you from the very beginning, that this area of research leads directly in what is usually called theological issues. And Cantor was indeed strongly involved with theologians in the Catholic Church and in other churches, pursuing the work initiated in this field by Leibniz. But in specific, I want to report to you about an event which linked my presentation directly with what will be discussed tomorrow morning. In 1869, the Pope Pio IX called for a new Vatican Council that provoked quite a reaction in the international Masonry, which called for a so-called Counter Council in Naples. Among the participants of that Counter Council, there were Garibaldi, Victor Hugo, etc. That is the so-called Mazzinian's network, as you will see and hear tomorrow. Now, this Vatican Council, which will create a major freakout also in Bertrand Russell personally, the reason of that freakout is that for the first time, in part, was admitted in the Church, officially in the Constitution, that God can be arrived at with the help of reason. Interesting, the cardinal who played a major role in that was Cardinal Franzlin. The same cardinal will define the social politics of Pope Leo XIII, and the one which had and will develop close correspondence and contact with Georg Cantor. The Catholic Church at that moment, or a group inside the Catholic Church, was responding not only to the growing positivism, but also to its twin brother, fideism, who negate any connection between reason and faith. So as there is no possible final formal function to describe the universe, at that same level, there is never an achievement.
Underlying this idea of adding facts on the basis of perception, which people often miss. Firstly, British empiricism. In British empiricism, there's no change in the underlying assumptions, the axioms adopted for knowledge. Secondly, there is no such thing as a fact determined by sense perception. The fact is that all sense perception is evaluated by the human mind on the basis of certain ideas in the mind. And those ideas do not come from sense perception, nor are they changed by perception per se. In fact, I may shock you by saying no idea ever came into anyone's mind from the outside, but all ideas are created from inside the mind. Therefore, no progress of knowledge comes as a reaction to sense perception. Progress of knowledge of the sort upon which our existence depends comes uniquely through the process of changing the basic assumptions upon which everything is based, including the way we evaluate so-called facts. We have historical proof that such changes are necessary for human existence. Every society we can document historically, which comes to rely on schoolboy notions of correctness of knowledge, on the equivalent of the Encyclopedia Britannica, is doomed to collapse. Now, this second, truer criteria of the truth, or of the development of human knowledge, which I indicate, presents us with a number of apparent paradoxes. One of these paradoxes might come up in the following sort of question. How can you prove a form of new knowledge which contradicts the basic assumptions of existing knowledge, or maybe your own assumptions? People will ask, well, this new knowledge or these new hypotheses, what can we check it against? Because people habituated to British empiricism and similar modes of schooling always want to check a proposition against something as a reflex to check whether it's the right answer. Well, and then you have another question or paradox. How can I check an idea to find out whether it agrees with human existence on this planet or not? How can I do that? Well, things are not quite so simple. And the problem lies elsewhere than the person is thinking that is formulating the question in that way. The problem is the question of the way of thinking. But let me intensify this paradox with a kind of example which I think will be familiar to many of you. We have someone in front of us, some person, we want to organize that person. And we say, look, the United States is becoming a pure British colony. And the person jumps up and says, that's the most ridiculous thing I've ever heard. What could be more ridiculous as the proposition that the United States is being made into a plantation of British controlled financial system, and that we're all being made slaves to that? So what do? Well, we try to prove what we said by going through the obvious selection of recent events, the clear evidence to prove it. But our friend doesn't see it that way. He or she interprets events in his or her own way. The same facts, the same perceptions are read in a different way, so as to not to arrive at the forbidden conclusions which his or her adopted assumptions forbid them to accept. So we see that no things such as distillation, precipitation, electrolysis, centrifugation, and so forth. Generally speaking, we start with any kind of stuff, and we do various things to it to see if we can induce a separation or differentiation of the original stuff into two or more new ones, each having clearly distinct characteristics. So in electrolysis, we produce out of water oxygen and hydrogen, for example. And then we take those new substances, which we produced by the separation of the first one, and we try to do the same thing with each of those two. And we keep doing that, trying to push the process to its most extreme limit of differentiation of matter. Now, through this kind of playful exploration, chemists, in fact, did arrive at a limit, as expected, in the form of what were sometimes called simple bodies or elements, substances which seemingly could no longer be caused to differentiate further. From ancient times, a number of such elements had been identified: iron, copper, tin, lead, mercury, gold, silver, sulfur, carbon. About 5 more elements were added in the period called the Middle Ages. And then, under the influence of Leibniz's work in launching an industrial revolution, there occurred, beginning around the 1740s, and actually during Leibniz's time, an explosive development of physical chemistry. So that at the time Mendeleev graduated from the main pedagogical institute in St. Petersburg, about 64 elements, chemical elements, were known. Now, I should note, however, before going further, that there are different opposing types of hypotheses associated with the term chemical element. British empiricism has insisted, for example, on the supposedly self-evident axiom or idea, which is still repeated, unfortunately, in much of our elementary education, that the elements represent unbreakable ultimate building blocks of matter, whose supposed quality of reality is borrowed from the baby's earliest years in the playpen. The great French chemist Lavoisier, on the contrary, adopted the more adult view that the chemical elements are singularities, are changes, moments of change, in a search not for ultimate building blocks, but for what he called the principles of matter, the principle of generation of matter. And Lavoisier emphasized that the separation methods of chemistry and the result of the so-called simple bodies depends on technology. It's relative, something that may appear to us to be an element or an indivisible substance, later may become divisible through a revolution in technology, which actually occurred through, to a large degree, exactly the work of Mendeleev. Now, I just want to note to you, in reference to what I said before, that this British idea of the building blocks of the unbreakable hard balls or whatever it's represented has the form of an axiomatic assumption. You can't refute it by any experiment or any so-called experimental fact, because if you succeed in separating what appeared to be an element, then they will simply say, oh yeah, well, we were just made a mistake in our facts. And this element collection of empirical facts, no matter how large, are going to do any good in this case. So we appreciate now the meaning of the statement that the British Empire, like the Venetian one, is an empire of the mind. These people are trapped. They are enslaved in the mind. So, what's the remedy? How do we liberate enslaved minds enslaved in this way? Well, of course, there exists a remedy. Otherwise, we wouldn't exist. Man was not born to be British empiricists. So, to find the answers, or to get on the right path, or fruitful path, I propose that we focus upon the crucial phenomenon called fundamental scientific discovery and its relationship to the desired effect of advancing human existence, that subject matter which is the center of Lin's work. And in order to do that, I want to discuss a kind of a case study. I want to take an example and use it as a kind of Archimedean lever, and I hope that in that way we'll be able to swing ourselves progressively upward to higher levels of insight as the discussion proceeds. Now, I've chosen for this discussion the case of the great Russian scientist Dmitri Mendeleev, born in the 1830s, 1834 I believe, and who died in 1907, and who is known primarily for his discovery of what he called the periodic law of the chemical elements, or perhaps more accurately, the natural system of chemical elements, which is not quite the same thing as the periodic table, which is a simple formal presentation of a result of that natural system. Now, a reason for choosing this particular example is that this discovery of Mendeleev's is central to the whole vast increase of the productive powers of human labor over the period of the last 100 years. That Mendeleev as a person, as a fascinating personality, displays in a very high degree the universal qualities of a scientist in the positive sense, in the second sense, not in the sense of an academic or schoolboy sense, but in the sense of a scientist devoted to building his nation, to building the world. Now, I'm not giving a presentation on chemistry here, and I'm not aiming at being precise in details of chemistry. I want to be as precise as I can about something else, and that is the internal process of discovery, or some crucial features of that process of discovery, which is our, let us say, our experimental data here. Not the chemistry, but the process in the mind. So I have to say, however, a few words about the field of physical chemistry to introduce this. At the time Mendeleev, Dmitri Mendeleev, began his scientific work in 1855, the central axiomatic assumption of chemistry was the notion of a chemical element. This notion is associated with the idea that we cannot differentiate or divide substance down indefinitely without encountering some kind of a limit or a boundary, or as we say, singularity. In the specific practice of chemistry up to the time of Mendeleev, the exploration of this area took the form mainly of what are called separation methods, chemical separation methods, which some of you know if you were fortunate or perhaps unfortunate enough to do school laboratory work in chemistry.
LaRouches method and the physical sciences. And before I introduce the speakers and a couple of messages, let me just say literally a couple of words. I think the way to situate precisely this topic, LaRouches method and the physical sciences, is to recognize that the breakthrough that Lyndon LaRouche made in the development of the conception of physical economy and the conception of potential relative population density as the fundamental metric, a breakthrough that he identifies occurring largely in the 48 through 52 period, with the culmination of his work on Riemann and Contour, is a breakthrough of the nature, and people should reflect, I think, on the presentations from this standpoint, that makes Lynn the last great thinker in the tradition of Plato, Augustine, Cusa, Leibniz, and so forth. And by being the latest great thinker in that tradition, he becomes, in that sense, the greatest thinker of that tradition. And from his standpoint, from the standpoint of his methodological breakthrough and his actual concrete scientific breakthroughs, we have to rediscover and rethink through all that has gone before to recreate that in our own minds and to allow us to use that breakthrough to develop fundamental science. We need to do this to be able to carry out the policies, the programs, the science drivers, the scientific research and development that is the future of the human species. So I think we have to look at the presentations from that intense a standpoint. Now, before I introduce the first speaker, let me read you a message. Greetings to the conference February 19th. We, students from Poznan, Poland, are acting now as the Polish friends of the Schiller Institute and are sending our greetings and best wishes for the future to all participants of the Schiller Institute conference in Washington. Unfortunately, we are not able to attend personally. The present situation in Poland is very complicated. Although our Prime Minister, Mr. Pawlak, seems to modify the looting policy imposed by the IMF and World Bank, there is still a very strong tendency of liberalism and monetarism in Polish political and government circles. Therefore, we see the necessity to present the ideas of physical economy in these decisive times. we are conscious that our ideas should be spread over the country. So we can happily announce that we just completed a new issue of the Polish newspaper of the Schiller Institute, Nowa Solidarność. Which means new solidarity. And we decided to publish it more regularly now. We are convinced that Polish cultural and historical tradition are a good background for our plans, and that we will find the support of many people in our country, which will make our work even more efficient. At the end, we want to express our congratulations for Lin's release from prison, and we wish a lot of success for his presidential campaign. Rafał Klopotsky, Andrzej Kozłowski, Małgorzata Krumplewska. Now I want to introduce Jonathan Tennenbaum, who one I know has just completed the recently published program for China. He will speak on axiomatic science and physical economy, a case study, Dmitri Mendeleev, and the discovery of the periodic law. Jonathan.
Thank you. The subject I wish to address this afternoon is reflected in the seeming paradox of the existence of two very different, mutually exclusive or contradictory definitions of truth. The first definition or criteria is that exemplified by the schoolboy idea of getting the right answer in the school or equivalent classroom. The right answer relative to some system of textbook knowledge, so that nothing can be accepted as true that contradicts the basic assumptions of that textbook knowledge. So this is the notion of truth expressed, for example, in the practice of cheating at examinations, or learning how to do the experiment so you get the answer which is in the textbook. It's the notion of so-called truth expressed by political correctness or correctness, that children should engage in polymorphous sexual perversion in order to demonstrate their acquiescence to what have been defined as the latest axioms of acceptable behavior. In each case, the truth is defined by non-contradiction to some collection of assumptions, either explicit or implicit, which are regarded as completely evident, unassailable, and beyond suspicion. Now, the second conception of truth, the true one, I should argue, is truth as measured against man's continuing existence on this planet. Truth measured in the great laboratory of human history, past, present, and future. So we test the relative truthfulness of our thinking by the success or failure of societies employing that mode of thinking to maintain and expand their existence. Of course, with the proviso that what may appear to be successful in the short term may be the shortest road, the surest road to destruction further down the line. Now, these two definitions or criteria for truth stand in an ironic, contradictory relation to each other. For it is historically demonstrated that in order for man to have existed up to this point, he had to constantly revise, often in a revolutionary way, his knowledge. So what was at one time defined as true or as the right answer becomes later the wrong answer. Entire chapters of accepted classroom knowledge are eliminated or overthrown. And without that, demonstrably without that, man could not have progressed to more successful ways of existing on this planet. Now, considering these historically demonstrated revolutions, I will speak of an example, we should beware of a trap, of the fallacy of British empiricism. British empiricism admits generally that knowledge does change, but limits the development of knowledge to adding new facts or correcting facts on the basis of sense perception. So, the British idea of truth is to get your facts right, according to the latest authoritative edition of Encyclopedia Britannica in the New York Times. Now, I said that there's a trap there. What is the trap? Well, there's a fallacy